A very good afternoon to one and all. Last time in the last session, I was discussing a little bit about multi-level inverter and how the advancement taking place in the field of multi-level inverter, and how could this switched capacitor type multi-level inverters came into picture. I have discussed regarding that also. And here, till this, I have told what are the different multi-level inverters in the last 1 decade. If you see the publications, most of them are based on uh, this multi-source type, where we need asymmetrical or symmetrical, whatever it is. We need multiple number of sources. So in terms of photovoltaic application or renewable energy system, if we see, the problem is we need to integrate multiple number of PV panels, and that will incur more control complexity. Also, the cost and losses will be much higher. So that is the main disadvantage of multi-source type systems. And whereas the traditional systems, definitely they require boost converters and traditional inverters also. That is again a problem. And also the voltage quality cannot be improved using the traditional inverters. So that, I have also introduced one of the switched capacitor type inverter, how that can improve the voltage quality, as well as it can reduce the cost by reducing the total number of sources. It means you can use only single source to boost the voltage. That is by employing the switched capacitor concept. And when you are employing switched capacitor concept, I have also highlighted one of the important thing, that we do not need additional capacitor voltage controller. So that is one of the biggest advantage of this type of system what I have proposed here, using switched capacitor scheme. And if you see the publications, you will find like in the last 4-5 years, people have started mostly working on switched capacitor types only. And now it is growing full interest in the field of publications in IEEE and IET. In most of the good quality journals, if you see, you will find most of the papers are related to switched capacitor type converters. So that is why I'm taking you through the most advanced type inverter topologies or multi-level inverters, where definitely if you want to do research, you will find a good chance on how to proceed with this. So till this I have discussed, and before I will start the hands-on session today, because I have also informed, I think we have informed everyone that we'll start the session, the hands-on at 4 o'clock. But anyhow, we got some time, 10 minutes today. So what I will just discuss one of our most recent publication on this switched capacitor type, because just excuse me, let me open this again. Yes. So slides are visible, right?
Yes, sir.
Yeah, great. So you see, if you have any questions regarding any of the things what I am discussing, you can keep it going on posting in the chat box, and so that I'll be discussing every other question at the end, because I cannot see I cannot see your questions in the chat box now while I'm presenting in my PC. So you can keep the questions ready so that we'll discuss each and every other question. So what I said before going to hands-on session, I said we'll discuss from starting from the software installation till the hardware implementation. I'll discuss each and every bit of it. I'll try to keep it very much clear and in detail mode, so that when you will try yourself to implement, when you try to implement in real time, in the experimentally, this type of inverters or whatever control schemes, if you want to implement, you will definitely find it very easy for implementation. So for that reason, I have taken one of the controller, that is the Arduino controller. So I will discuss later on about that. Before that, as I have said, I will tell you one of the important reason behind this growth in switched capacitor type inverters. Yes, so this circuit on the right hand side, if you see what I have highlighted last time also, this circuit, how it works, this voltage source, or if you can think of it, this is like a PV panel. So that is charging the capacitor. Only one capacitor is then in this circuit. So that is charging the capacitor when switch S1 is turned on. And when switch S2 is turned on, that capacitor is getting discharged, and so that voltage and this capacitor voltage, so they are both getting added to get the output. So you think how the voltage steps are produced. In the first step, at let's suppose this is alpha 1, you just think of this output voltage pattern what I have shown here. So at alpha 1, the first angle, if you see, I will switch on switch S1. If I switch on S1, what will happen? The capacitor will start charging, right? So as capacitor is started to charge, and some current will also flow if T1, T2 are on in the positive half cycle. Current will start flowing through T1 and T2, so that the positive half cycle first step, because only V is connected to the load. If you see in that way, in the circuit flow path, the capacitor is getting charged in this path and in parallel, obviously, and B, the supply voltage, is also connected to the load through T1 and T2, right? So because of that, the output voltage is V. Then at alpha 2, if I now switch on S2, what is happening? The capacitor is now able to discharge in series with the source. So in series with the source, when capacitor is discharging, that voltage, both the voltage will be added definitely. So the input voltage source V and the capacitor voltage that is earlier charged to V, now the both will be added. So the output voltage will now be 2V, right? So this circuit will also produce 2 times the voltage. So voltage boosting is possible. Capacitor is not does not require any voltage balancing circuit. No sensors are required. Switch count with comparison with the conventional circuit has been reduced. So with respect to that, this is one of the important aspect, no doubt. But still, what is the problem then? Where the problems comes is when you try to again cascade it in the same fashion as the conventional circuits are cascaded. Now you think of cascading this circuit to increase the number of voltage levels, because you are designing a multi-level inverter and your main focus is to increase the number of levels also, right? That is also one of the focus. So when you integrate or cascade it in this way, so the circuit diagram what I have shown here, if you can see, this is just the cascade version of the module what I have just now explained, right? So when you cascade it like this, what will happen is, again, no doubt the number of levels now it is 9. If you see on the right hand side, the output voltage of pattern of this is shown here. So how it is creating a 9-level output? It is very simple. I think if you have understood the previous circuit operation, you can easily understand this one also. See, there are 2 voltage sources. If I take both are equal, let's suppose, in that case, the first module that is charging the capacitor to the same voltage source, and this capacitor, second capacitor, is also charging to the voltage source. So what is happening? The total voltage now available across the load will be this input voltages V2V, and the capacitor voltage again V2V. So 4V output will be there, right? So obviously again using this module, you will get 4 steps at the output, and for it means what? 4 steps in the positive half cycle, 4 steps in the negative half cycle, there is a 0 level. So it means that is a 9-level output. I said in the last time also I have discussed how to calculate the levels. If you see output voltage form of a multi-level, those who are not working on multi-level inverter, maybe they are somewhat confused how I am telling you this is as a 9-level or 5-level or 7-level. So it is very simple. How many steps in the 1 half cycle if you count, you can just double it and plus add it with 1. Because if there are 4 steps in the positive half cycle, so 2 times the number of steps plus 1 will be your output voltage levels, right? Because in the positive half cycle, negative half cycle, there are same number of levels, and there is a 0 level, I said. That is called as multi-level. There from 3 level, the multi-level concept came into picture, right? So here again, what is the problem came that I have highlighted here in the red color? There are still multiple DC source requirement, right? If you see, there are still multiple DC sources are required, because now you have cascaded and there are two DC sources required. It means two number of PV panels separately we need to connect. Then again, we need to control both the PV panels separately. So to avoid this problem, so what researchers, some of the researchers have proposed very recently, if you see, they proposed different circuits. These are all very recent circuits developed in the last 2-3 years. If you see, they are all containing only single DC source. Here in the first circuit, if you see, there is only one big single DC source. Second circuit, again, if you see, there is only one single DC source. And all the circuits, all the 4 circuits I have shown here, they require only a single DC source. And also, what is the advantage is that you can extend it to any number of level. The dotted lines, what is shown here, if you see, that means it can be extended to any number of level. That is, n number of level can be extended. You can produce 11 level, 13 level, 15 level, 17 level, like that. You can go on increasing the number of levels by just cascading or by just integrating these modules, if you see. So wherever there is a dot line, if you see the first circuit, you see the dotted module, that is the basic module. If you see, that basic module is going on cascading, right? So what it is doing is this load side 4 switches, the H bridge, what I call it as H bridge, because this is just creating the polarity, positive or negative, right? These 4 switches are having no use, only to generate only to reverse or the polarity, you can say, positive half cycle and negative half cycle. Because this side circuit, you can say this is the DC-DC module, right? Whatever DC supply is there, this will create only DC output, only positive output. But how to get a positive and negative? Because we want to get from inverter AC output. So for that polarity changing, you need to operate this, you need to connect these 4 switches, so that when 2 diagonal switches are operating, it will give you the positive output. When another 2 diagonal switches are operating, that will give you the negative output. So similarly, all these circuits are designed. And if you see what I have highlighted here, one important point, that is single DC source. So using only one single DC source, you can extend it. But still, there are some other problem. I have highlighted that point in the last session, that is the voltage stress across the switches. If you remember, I told what is the standing voltage. Can anyone tell me what is the standing voltage I have informed in the last session? No one. I think my voice, you are getting my voice, right? Or it is disconnected?
Sir, your voice is clear, sir.
Okay, thank you. So standing voltage, in the last time I've highlighted, what is this voltage stress or standing voltage? See, you take one circuit, the basic circuit on the right hand side, right? That is your switched capacitor type circuit here. And what is the standing voltage? That is nothing but when the switches are in turned off condition, when the switches are not operating, at that time, how much voltage stress it is withstanding, that is called as the standing voltage. But you will find, if you read the recent publications, whatever recent publications you download from IEEE and read it, you will find a term total standing voltage, or sometimes they write it as total voltage stress. So TSV, total standing voltage, the TSV, what is that TSV? What is the total standing voltage? That is nothing but I told you, the standing voltage across each switch, if you take into account, and if you add it, the total standing voltage will be the sum of standing voltage across all the switches in a circuit. So here, to analyze this circuit, let me analyze this circuit so that you will be very much clear with that. Now you think, I said here in the first level, what I am turning on, S1 and T1, T2. When I am turning on S1, at that time S2 is off, right? Because S1, S2 cannot be turned on at a time, otherwise the source will be short circuited here. So you cannot turn on both S1 and S2. It has to be turned on asynchronously, right? Simultaneously, the turning on is not possible. So if you turn on S1 in the first step, S2 has to be turned off. If S2 is off, that time, it means when it is off, it is blocking some of the voltage, right? When it is off. And when it is on, it is conducting, current is flowing through it. That is the basic concept of network theory. I don't want to go through it. So if the switch is S2 is not conducting that time in the first step, what will happen? how much voltage it is blocking. So that is this same voltage what is connected here, because it is here, it is only one supply voltage V is there. So this switch S2 is now blocking only V, voltage V. Similarly, in the second step, if you consider, the switch S1 is off and S2 is on. S2 is on. Again, if what how much the S1 is blocking, the switch S1 is blocking. If we apply simple Kirchhoff's law, you can calculate how much the voltage S1, how much the voltage appearing across S1 when it is off. That is again the same voltage V. So what it means, what both switch S1 and S2 are facing or withstanding the same voltage, input voltage V, when they are not conducting. That is clear. Then all the other four switches, you now will understand why I am telling to avoid this H bridge here. H bridge is definitely required to generate this AC output voltage, but you can make some arrangement in the circuit such that you can avoid the H bridge, so that to reduce the standing voltage. See why and what will happen here. This blue point and the red point what I have highlighted, at these 2 points, what is the maximum voltage? At these 2 points, maximum voltage is 2 times the input voltage, right? Because maximum voltage, when I say when S2 is on, at that time these 2 points maximum voltage will be 2V, because capacitor voltage and the input voltage is added. So that 2V is now appearing across all the 4 switches, right? So total standing voltage in this circuit, if I want to calculate, now that will be 2V times all the 4 switches. So that is 8V plus these 2 switches VB, that is 10V. Total 10 times the input voltage is the total standing voltage. Clear? So total standing voltage is 10 times V. That is not a problem. But the problem is these 4 switches. These 4 switches are blocking the maximum voltage, whatever appearing across them, right? So maximum voltage is 2 times V. That is appearing here. Now that is this 4 switches S2 is stand. It means now you consider, or now you think of this type of circuits, what I've shown. Now in this circuit, if I just go on cascading the modules like this, and all this voltage will be now added at these 2 points, right, across the H bridge. Now that will appear across these 4 switches. So because of that, what will happen? Standing voltage across these 4 switches will be maximum. So we need to avoid this kind of configurations. So without any delay, I will introduce one of the topologies just now what we have developed here in the laboratory. I will also go through this detailed experimental investigation because I told you I will be discussing about hands-on. So at that time, each and every parts of this circuit and all I will discuss. So here, this type of circuit I have developed here with one of my co-author, Prabhat. He is also, I think, connected to this session maybe. And we have developed here in this laboratory. You can see there are only 13 number of switches and there are 3 number of capacitors are there. And the advantage of this circuit is that we have connected 3 capacitors, but all the 3 capacitors are self-balanced. So it doesn't require any closed loop voltage balancing controller. That is the advantage. You can see there is only one single source. From one single source, we are able to achieve 6 times boosting ability. So voltage is boosted to around 6 times here. If you see, the voltage boosting is about 6 times. So if you can boost it to 6 times, you do not need any DC-DC converters in the photovoltaic system applications. Here, to clarify how the current flow path is, in each step, you can see the output voltage. I have shown it here in the left-hand side. There are 6 steps in the output. In each step, when producing the first step, how the current will flow from the source to load. When producing second step, how the current is flowing. So each and every step that is being analyzed here. If you see in each step, here some blue color lines are there. Here in the second level, you can see the blue color lines here. That is showing how the capacitor is getting charged, right? No doubt the source is producing, source is connected to load, and sometimes this 2 VDC is produced at the load. But at the same time, I am also charging the capacitor C2. Similarly, each and every capacitor in some of the steps they are charged, so that you do not need additional voltage balancing circuit, right? So what is that additional voltage balancing circuit means? You need to control the switches such that current will flow through the capacitors and you can maintain the charge. In one fundamental cycle, if you are able to maintain the full charging and discharging of a capacitor, then you can guarantee that capacitor voltage will be balanced definitely, right? So here some of the very technical calculations we made to design it appropriately. I don't want to go through because this is, if you read the papers very clearly, then only you can understand. And this here focuses how to design the capacitor. I'll just highlight you how to design the capacitor or how to choose the value of the capacitance in real time. Because in real time, capacitor is facing the ripple, right? Because capacitor is charging and discharging, that you also need to focus. When capacitor is charging and discharging in each cycle, it means you cannot maintain a constant voltage. There might be some ripple like this. So this ripple in voltage across the capacitor, if you want to minimize, let's suppose I will consider the ripple in capacitor voltage is 5 to 7%. Based on that, you can calculate. So here I have taken 4 different values of the ripple. You can see 5%, 7%, 10%, 15%. Similarly, for different parameters, like with respect to output voltage, we have first calculated C1, C2, and C3. I have said, right, 3 capacitors are there, C1, C2, C3. And C1 and C2 here, I will just highlight one point. Both C1 and C2 are getting charged to V. Remember it. And the capacitor C3 here is charging to 3 times the V. How? Now that is because of the both the capacitors voltage and the input voltage. That V, both all 3 are getting added together to charge this capacitor C3. And because of that, this capacitor C3 is charged to 3V. Now you add the total voltage. Total voltage will be supply voltage V. Both the capacitor, this C1 and C2 are V, so 3V, plus the capacitor C3 is 3V again. So 6 times the voltage we are getting. Very simple, right? So as I've said, both capacitor C1 and C2 are getting charged to V. So we have considered they are all equal, right? And considering the discharging cycle, up to what time the capacitor is getting discharged, maybe in the paper, if you will find very detailed explanation. Discharging cycle is what, and all those things you need to understand very clearly. So up to what is the maximum discharging time of one capacitor, that we have considered to calculate. And obviously frequency, capacitor voltage, load current, these parameters are considered all this to calculate. So what we have done here, we have taken a graph with respect to power factor, with respect to output voltage. If you see here, at 5% or 5% to 7%, you can consider a limit to design a capacitor or to choose the value of capacitance. So within 5% to 7% value, if you see, the capacitance lies somewhere here, right? So that is showing the value of capacitance can be chosen around 3000 to 4000 microfarad, because these are in millifarad. So it means this is 4 millifarad, means that is 4000 microfarad. So in that range you can choose, and C3 can be chosen in that range also, in that respect similarly. So taking into account that, we have taken the values of the capacitance. I will show you later on the results. So here we have done a thorough comparison with respect to various parameters. If you see here, we have compared first different 7 level topologies, different 9 level topologies, and there are very recent 13 level one, and we are also getting 13 level, right? So our 13 level inverter is compared with all the different topologies of different sources. You see, with respect to number of source, only one source is required. Compare with other topologies. These references you can find it from the paper. I'll show you what that paper is. And here again we have compared with respect to number of switch, number of driver, number of diodes, number of capacitors, what is the voltage boosting, because here I have told you what is the voltage boosting, that is 6 times the input. So that also you need to consider. And one more term I have introduced here, that is nothing but the total standing voltage, and TP stands for here per unit, right, per unit value. So do not confuse, this is nothing but a total standing voltage, that also we have calculated. Then to one important factor we have considered, because after considering all these terms, it may be confusing which topology is better. So for a fair comparison, we have taken another factor here, cost factor. If you see that cost factor we have defined here, and the cost factor has been calculated taking into account all the terms. So you can see there is minimum cost factor. This is not the cost of an inverter, right? Do not confuse with the cost of exact cost of an inverter. This is the factor we have taken into account for a fair comparison. So that is cost factor, and you can see that the cost factor is very, very minimum with comparison with all the different recent proposed topologies. So that shows how superior the proposed topology is. But still, I will tell what is the disadvantage of this circuit, and that how we came up, we have overcome this the problem with this circuit in another circuit. I'll also show you that one. You can see here some of the key results, right? With change in modulation index, when there is a sudden change in load, you can see there is a the pink color graph, the load current is suddenly rising here because of the change in load. Clear? And here you can see there is a sudden drop in input voltage. When there is an input voltage decreasing continuously, because of decrease in input voltage, the 13 level output is still maintained. You can see the 13 level output is still producing. But whereas because input voltage is reduced, obviously the total output voltage will get reduced, right? So here we have taken 30 volt. You can see the input voltage, we have taken 30 volt. If you take 30 volt, because I have said it is boosting to 6 times, you can verify it around 180 here, we are getting the output peak, right? So it is boosting to around 6 times the input voltage very clearly. And the important thing is you can see both the capacitor C1, C2 here, C1, C2 are getting charged to the same 30 volt, because I have said you C1 and C2 both will charge to the same input voltage, and whereas C3 will charge to 3 times the input voltage. So it means it is charging to around 90 volt. And as I have said, there is some ripple in the capacitor voltage. That ripple will be definitely there in practical conditions. You cannot avoid the ripples. If you take very large size capacitor, maybe ripple will be less, but it will incur more cost or losses will be higher. So that also you need to consider. So taking into account all these points, again, we have developed the hardware, what I have shown in the previous slide, maybe, yes, here. So this hardware setup, experimental setup, clearly tested with different dynamic test condition. If you can see, first thing we have tested with modulation index change, where the output voltage is only changing, there is no other change. Capacitor voltage are still maintained. Here at this point of time, load current is changed in the second case. When there is change in load current, you can see resistive to inductive, how the current is changing, whereas there is no change in the output voltage. Again, there is another case here. In the fourth case, you can see with non-linear loads, whereas there is a presence of non-linear load, you can see the load current is not sinusoidal at all. If there is because of the non-linear load, right? Not sinusoidal, it is somewhat kind of step type. So it is producing, you can say, harmonics because of the non-linear load. But what we want to highlight here, the output voltage, there is no change. Still we are able to get 13 level output. With respect to sudden change in frequency, because if you go to some of other parts of the world, you will find there is a difference in the frequency. In the India, it is 50 hertz, maybe in US, it is 60 hertz, like that. And one more important point I have highlighted, I think, in the first session, when you go for a development of switched capacitor type, it is not only for photovoltaic system. There is another application, high frequency AC power applications. In high frequency AC power applications, this switched capacitor type inverters are now very widely used, because you see, if you see clearly, I do not know how much the picture is clear, but if you see here at this point of time, when there is a change in the frequency, the capacitor voltage ripple is reduced to negligible, maybe, because the frequency has been increased to very high, right? So because of the change in frequency of the inverter, output voltage is no doubt produced, whereas the capacitor voltage ripples are getting reduced. So because of very less ripple in the capacitor voltage, there is no problem in operating as a high frequency AC source. So that is one of the prospective application, and that's why we have also tested with different frequency. Also, there are 2 tests conducted at high switching frequency, because if you see the output pattern, you will clearly find a clear what is that called, distinction between these results. All these 4 results what I have shown here, these 4 results are fundamental frequency switching control outputs, and these 2 results are high switching frequency control. Because of high switching frequency, you can see the pattern, how it is, the output voltage pattern, right? This is the fundamental frequency output. We'll discuss some in more detail about the PWM control scheme in the hands-on. Within 2-3 minutes, I'll start it, the hands-on. And you can see there is a load change here. You can see the output. So with the dynamic test condition, I just want to say this inverter has been tested. This is some of the power quality parameters, how the inverter efficiency and all. We have also tested the losses, power losses with respect to different output power. So I'll not go deep into it. You can refer the paper. This is one of our most recent paper. Here, as I've said, again, we are using the single input voltage source. But what is the advantage of this circuit, I can say? Here, if you compare, this is again producing the same 13 level output, you can see. But here the boosting has been reduced to around 3 times, right? It is boosting to only 3 times. 3 times boosting is also not very, like, you cannot say it is not good, because 3 times it is boosting. So you can still avoid a boost converter. Whereas what is the most advantage of this circuit is there is not at all any H bridge kind of thing where you require at the end of the, or at the load side, you can say. This H bridge is avoided here because so that as it is avoided, you can also see the standing voltage is very, very reduced in the comparison. So this kind of bridge, the diagrams is not very clear, but you can, I think, understand the point what I'm telling. So this kind of bridge circuit where 4 switches are required, that is avoided here. And the polarity still, it is producing the IC output. If you clearly try to analyze the operation, I think you can easily understand how this circuit is working. So here I have shown you in detail the positive half cycle operation and negative half cycle operation. And also a comparison has been done. You can see a detailed comparison with respect to every other parameter. Here, I have introduced 2 different new terms, I can say. This is nothing but the DC source, switch, diode, capacitor. And here you can see there are 2 different terms. One is the how many number of conducting switches in the number of semiconductor switches conducting in the conducting path, you can say, right? Conducting path means this is, let's suppose you can take any level you can consider, and you can see how many number of switches are conducting. So likewise, I've taken here, you can see with respect to first number of conducting switches, the minimum number of conducting switches are there in the proposed circuit. So that shows the conduction losses will be very less. If you are designing a power electronic circuit, losses are very important. You need to think of conduction loss, switching loss. So losses will be very less. Another term over here I have shown NSS. NSS is nothing but the number of switches facing stress less than 1, right? Facing stress more than 1. So here you can see there are only 2 number of switches which are facing stress more than 1. Whereas other circuits, if you see 8 number of switches facing stress more than 1, 6, 15, which is very high. Whereas some 2 circuits you can see, you can also very clearly identify it is 0 here, but you can see other parameter. Not that only if you maintain the stress very less, it is good. You can see other parameter, the voltage gain is only 1.5 times, but whereas in our circuit it is 3 times. Whereas here, in the second case where it is 0, you can see the number of switches 29, whereas we have reduced to only 12 switches in 13 level. So if you require only 12 switches in 13 level, definitely the you can see it is almost halved, right? Not halved, even 3 times lesser than the other proposed circuits. This is also very recently proposed circuit. You can see the reference number. It is in 2019, I think. So within like this is very recent papers compared here. All the topologies, you can see again the dynamic test case results in the experimental test case. It's with RL load. This is with again R to RL when sudden there is a load change. Here now in this time, if you submit any paper anywhere, you will definitely find reviewer comments on dynamic test case operations, because they want you to test everything in dynamic operations. So that is why these tests are conducted in dynamic test case. And if you can see clearly, I will highlight one important point here, one important observation you can say. Here you can see the pink color graph, right? That is the current waveform, which is changing accordingly with R and RL load. With R load, that is following the Ohm's law. So whatever the voltage pattern, same pattern, the current is following. With RL load, when there is an inductor presence in the circuit, that will behave like a low pass filter. And because of that, the current is more or less sinusoidal, right? Clearly sinusoidal, you can see. So because of that, what is happening, important observation what I've told you here, because of sudden load change, you can see the voltage ripple across the capacitor. These are the voltage ripple across the capacitors. You can see the voltage ripple. The voltage ripple, if you clearly see, there is a large drop in the voltage ripple. Why? Because there is a change in the loading. So whenever there is a change in load, definitely ripple will reduce, and you can correlate with the graphs just now. Before some 2-3 slides I have shown you with respect to power factor. I have shown one of the graph with calculation of capacitance with respect to power factor. It means what? Power factor is changing. When there is R to RL load change, power factor will definitely change. R means that is unity power factor. RL load will be, there is power factor around, here you can see the in the power quality analyzer, power factor is around 0.93, right? Gamma is the power factor here. So power factor is around 0.93. It is reduced to 0.93. When there is a change in power factor, there is a change in capacitor voltage ripple. We can see in the next presentations more clearly. So this inverter is also tested with high switching, low switch, or fundamental switching, and also verified here that 3 times boosting. You see, I have taken 60 volt input voltage. Voltage is 60 volt. What I am getting here at the output is the peak voltage. If you see, around 100 volt per division, so I am getting around 180 volt maximum peak. So 180 volt means that is 3 times the input voltage, right? You can refer my 2 of my papers, recent papers. So as a summary to this, before starting the hands-on, I can tell you here important points where you need to consider for designing a switched capacitor inverter is all this term. All this. Not only reducing the switch count or number of DC sources is important. With respect to that, you need to also focus on how to reduce standing voltage. I said standing voltage is an important factor. What is this PIV? Nothing but peak inverse voltage. PIV is nothing but in a circuit, what is any switch which is facing the maximum stress, that is the peak inverse voltage. You understand? Total standing voltage is the standing voltage across all the switches. You have to add it up. Peak inverse voltage is any one switch which is facing the maximum peak voltage. Self-balancing, you need to consider voltage balancing should be automatically, it should balance or inherent. You should not add any complex voltage balancing controller because that will again cost more. Then voltage boosting also you need to consider either 2 times, 3 times, 6 times. Now it has been proposed very recently 6 times. Then you need to also consider the load handling ability. Linear load, non-linear load, R load, RL load, everything it has been tested. Then the power loss and efficiency. These two are also very important terms, right? So you need to consider all these factors, I must say, for designing a efficient or an efficient switched capacitor type inverter, right? Also with respect to one of the important point, what I have not shown is the point what I have highlighted you earlier, that is extending to different level. If you want to extend the circuit for higher number of levels, that is also one of the important point. So with this, I will tell you here what are the important points, important papers. You can focus on these first 2 papers are based on only harmonic elimination control, different new algorithms. New proposed inverters are there, but both are multi-source type. No switched capacitors are involved. There are other 2 papers in IEEE transactions on circuit and systems express briefs. You can see these 2 papers, what I have explained just now, about switched capacitor type, 6 times boosting and 3 times boosting. You can also refer to this IEEE transactions. There is another IEEE transaction from one of our co-author, the Prasad. You can see this is an integration, I can say, for both the circuits. Switched capacitor type and the diodes, switched diodes, everything has been combined here. But we have not used any complex voltage balancing controller. That capacitor is still getting charged automatically here also in this circuit. That is also one of the important paper where we have also tested the inverter in integration with photovoltaic system. And what I have told you, another important point, extendability. We can extend to any number of level. That is there in another recent IEEE transaction paper. So you can follow all these papers to know more about the research work. I will not go through it again. So let's start the session, hands-on session. See, I will try to detail you as much as possible regarding the how to proceed from software to hardware. I think most of the participants, they might have worked with hardware. I don't know exactly. Or you might have tried the simulations only. But those who are trying with only simulations or very good journal publications or publication reputed journals, you cannot do without any experimental work. So I will definitely tell you here by the end of this session, you can, if you really want to try the experimental thing with this Arduino, because I will highlight only Arduino. It is not good to, if I directly highlight this FPGA based controller or DSP or DSpace. There are this type of controllers also available with us, and we have also a polarity setup. If I show you, because this will look good, no doubt, the DSpace controller and everything, definitely it will look good from outside, but when you try on your own, definitely you will suffer a lot, and you will, if you are thorough with this, definitely you can do it. But if you are not thorough, I can definitely guarantee you that you will have problems when implementing in real time. So what is the this software we generally use here is the MATLAB Simulink, and there are other scholars, they are using different softwares and for designing the simulation circuit. So and to verify in real time, as I've said, DSpace, FPGA, and DSP, we have Opolati, we have now like almost all these controllers in our institute. Different scholars are using it, and I don't want to go through those kind of things, but what I will tell you here in the hands-on regarding the control implementation from software to real time, you will definitely understand how to integrate this Raspberry Pi, this FPGA. FPGA, obviously, you need some additional softwares like Xilinx and all. Here also, we need some additional software, but that is very simply, easily available at free of. You can freely download it from the website. I will show you where to download, how to get it, everything, and definitely you can understand. If you want to link with the DSP, also you can do the same way, right? So that is why I'm highlighting here one way, but this will lead you to the multiple ways you can do the real-time work. As like you, if you want to test the inverter or any control algorithm, if you want to test, if you are having a complex control algorithm, definitely you need to go for DSpace, DSP and all. You cannot try with Arduino. But to start with, you need to start with some low cost controller, I must say, so that you will be able to get clear with it, so that you can test the design systems, right? I must suggest that one. So till now, before I go to immediately to this hands-on, I just want to know if anyone is having any experience with experimental work. You can tell me if anyone has done a rigorous experimental tests, what like I have shown you just now in this operations. Anyone who can voluntarily tell me if they've tested in real time? Okay, so shall we proceed, or any doubt till now?
Sir, please explain overview of at least all controllers what are used in power electronics to generate
Yes,
pulse width
yes, yes,
signals.
yes, yes. Very good questions.
Why? Because means we have
After
sir,
this, immediately I'll start with the control scheme only, overview of control schemes used for controlling the inverters. Definitely, I'll
yes.
do that.
Why? Because means whenever entering into the hardware, many members doing DSP pick like that saying, sir. But we don't know, sir.
Yes,
Which
yes.
microcontroller, which language,
That is what
which
I want a clear picture of from you, because
uh,
whether you have tested with real-time controllers anytime or not. That is why I have asked you
no, sir.
that
Just
you
now
have.
I am trying an ESP32 microcontroller, sir, using Arduino IDE. Okay, but I
Okay,
am
great, great.
unable to generate three-phase pulse with that means sinusoidal PWM, sir. That is, I am unable to understand the how to generate this.
Okay, thank you. Okay, no problem. I will do that.
Yes, sir.
Here, I think after this, you will get some clear picture at least to implement on yourself. You can try it immediately. I must suggest within like a few days, you must try it. Otherwise, if I tell you something and you will forget definitely after 2 3 days. See,
No, sir. If you tell
no,
me,
no
sir, I
problem.
will.
I will share the slides with you,
Uh,
and I will try to make it as much as simple so that you
uh,
can install yourself and you can implement. Anyone else to share with your experimental real time experience? or else I will proceed otherwise. Any questions? Let me see in the chat box. There is no questions. Very good. I think you have all understood everything. And any other questions from any participants, or else I will move to the explanation of this. No questions. Okay, thank you. I know the time is up to 4:30, but we have already informed in the email today's session will maybe up to 5 o'clock. So if no problem, if you are interested to listen to this real-time testing, how can be done, definitely you can attend it.
Sir, we listen until 5:36 also, sir. No problem, sir.
Okay, thank you, thank you.
Why? Because means controlling scheme is very important, sir. To design any hardware, sir, that's very important, sir.
Sure. So what I'll do is I will also highlight here to implement one of the controller. Okay,
Yes,
how
sir.
it can be done,
Yes,
so that it will be easier for you. But I must say, after the end of the session, we'll discuss whatever doubts are there. Okay, let me
Okay.
start here.
Okay, sure, sir.
So as I've said, this multi-level inverter implementation, I will focus also with photovoltaic system. We'll see in real time how it can be implemented. Before that, let me start with the control schemes. So as sir have skipped the some of the slides, what are the different control schemes? It looks all theoretically good, I must say, right? Theoretically, we have studied from book and all power electronics basic books, high switching frequency control, fundamental switching frequency control. We have studied from book. It looks fine with theories. And if you see the carrier-based controller schemes, these are all high switching frequency control schemes. What I have highlighted here, level shifted, phase shifted, both are carrier-based control schemes. You can say they require different number of carriers and sinusoidal reference to get an output. These are generally closed loop type PWM control schemes employed, and in real time also it can be tested very easily. Fundamental frequency control schemes like selective harmonic elimination control, nearest level control, space vector control. I am not talking about the SBPWM, space vector PWM modulation technique. That is no doubt a high switching frequency one. There is another control called space vector control. That is one of the fundamental frequencies. So like this, there are varieties of control scheme tested. So what is this level shifted one? Just few points I'll tell you, then we'll start. So here level shifted, and you can see one of our review paper last time also I have highlighted. Here I think in this slide we have given somewhere the difference. And you can see these are all high switching frequency PWM control schemes. See the output of the multi-level inverter. This is shown for a 7 level. Again, I am telling you how I am calculating the number of levels. 3 levels on the top, 3 levels down, there is a 0 level. So 7 levels. If there are 3 steps, you can say 2 into 3 plus 1. That is how I calculate. So there are 7 levels at the output. You see the principle of operation is shown in with respect to block diagrams. The level shifted, phase shifted, and the space vector one. So here, obviously, these are all high switching frequency control schemes. Oh, if there is a high switching operation of inverter, that will incur more loss, right? So because of high losses, power losses, the total loss, switching loss, if you calculate in a circuit, that will be higher. If total loss is higher, obviously efficiency of the circuit will reduce, right? But there are different other advantages when you try it your own, the switched capacitor type, what I've introduced just now. When you try it your own, you will definitely get new conclusions from that. The reduction in ripple, then the charging current. About that, I have not discussed here because that are some of the very advanced things I have not discussed here. That have been highlighted in the papers. If you follow the papers, definitely you can understand. And here, this is a high switching frequency PWM type output, as you can see, right? So these are different PWM control schemes. I will not tell you here because from the block diagram you cannot understand. We will see in the implementation itself how it can be done. This is again fundamental frequency type switching control. You can see. So in the fundamental frequency type switching control, you can see the selective harmonic elimination. I will explain one in detail because I personally have worked on selective harmonic elimination control, different algorithms we have developed here. Nearest level control, one of the switching, another fundamental frequency switching control scheme, which is much easier to implement, no doubt. but you cannot guarantee on harmonic control, because only selective harmonic elimination control, you are selecting third harmonic, fifth harmonic to eliminate, and you are doing the work. So that is different. The nearest level control is something different actually, and different means you cannot have a control exactly on which harmonic you want to eliminate or you want to control, right? But this is also one of the fundamental control scheme. This is space vector control. This is also another control scheme. So these are different types of control scheme we have also discussed in one of our paper. If you see here, to understand the concept first, I have highlighted in the first slide, in the just previous slide, high frequency PWM control scheme means what? Why it is called as higher frequency? That frequency term itself comes from the frequency of these carrier signals, right? So there are multiple carriers here I have taken. You might have been confused with why I am taking this carriers and all. These carriers, and there is one reference, right? I will tell you why I have taken it. This is for generation of a 5-level output. See, if you want to produce a 5-level output, till now what I have discussed like this, a 5-level means there are 2 steps on the top, 0 level, then there are 2 steps on the negative polarity, you can say. So this kind of output is there. So if there are 5 steps in the output, right? Is it that clear? So if 5 steps in the output, let's suppose this is V, this is 2V steps, 5 steps in the output. So you need 4 carriers, or else you can take 2 carriers also. You can just change the carrier signals, what is that called, the magnitude and all, so that you can do it. So this type of this carrier signal, the triangular signals are called as carrier, and there is one of the reference. The reference, the frequency of the carrier signal or the triangular signal, that decides at how much frequency the switching has been done, right? That is the switching frequency. Clear? So here if you see the difference between this phase disposition, phase opposition disposition, POD, alternate phase opposition disposition, till now if you see all these publications and papers, you will find there are various papers till now, they are using these 3 control logics. Phase shifted control scheme has been avoided most of the times, because you see there is a multiple number of carrier, very large number of carriers are required in this phase shifted PWM control scheme. No doubt introduced by some of the researchers in the starting, they have used this control scheme for power balance and all these things in the cascade hybrid multi-level inverters, but still they are now, people are avoiding it, because the control scheme is somewhat not easier, or you can say more complex with respect to all these 3 types. These 3 types are almost all similar, but what they have done is here, if you clearly see these 2 carriers on the top here and these 2 carriers on the down, they are all in same phase. That is what phase disposition PWM control scheme, right? All in phase. Clear? And if you see the just a second, the second type, phase opposition disposition, POD, you can see the positive 2 carriers here, they are in a phase. Other 2 carriers here, they are in other phase. So there is a 180-degree phase shift from the carriers. So that is what is POD, phase opposition disposition. There is another one, alternate phase opposition disposition, that is also proposed by another researcher. Here if you see, each carrier is alternated. See the first carrier and the second carrier, they are in 180-degree phase shift. See the third carrier, the fourth carrier, they are again 180-degree phase shift, right? So all these 4 are alternatively, they are shifted. And you can see, when I say shifted, they are shifted by level, right? The magnitude or level, you can say. They are not shifted by phase, like here in the 4th case. In the 4th case, they are shifted horizontally. What has happened here? Just a second. So here if you see, they are the carriers are shifted horizontally, whereas here if you see in these 3 cases, the carriers are shifted vertically. So this is also otherwise called as, you can say, vertical shifting PWM control scheme, and this can be called as, the phase shifted one can be called as horizontally shifted PWM control scheme. So in all these control schemes, to implement, what you need to do is you need to first generate a reference, that is sinusoidal signal. Then you need to generate some carrier signal generation also. First you try with simulation, I must suggest, because if you really want to develop an hardware, you must try the simulations very clearly. Simulation has to be done properly. If simulation is done, you are halfway done actually. You can do anything then after that. And just trying simulation in haphazardly will not do anything. You need to understand the concept behind the simulation, what it is doing. And you need to test the inverter first in dynamic condition in simulation itself. Then you can go for real-time one. So this reference and the carrier, if you compare, that as sir was also telling, that will give you one term that, as we all of us know, that is, sorry for this writing and all, but that will give you your modulation index, right? The reference and carrier signal amplitude if you compare. So this modulation index variation, you can do the tests by varying modulation index. So not taking too much time on this high frequency PWM, because I will tell you about this fundamental one. This fundamental PWM control scheme. This is also one of our paper. One of our paper, I can say here, you can refer this paper in IEEE Transnational Industry Applications. We have focused on 7-level inverter. So you see, if you, I think I've not shown a 7-level output here. Yes, correct. So this is a fundamental frequency output, right? And you can see this is the grounded signal, 0 signal here. So there are 3 steps on the positive, 3 steps in the negative, and 0 level. So this is producing a 7-level output. So in this 7-level, you can see clearly how many number of instances or switching angles are there. There are 3 switching angles if you want to calculate. Clear? Because if you know these 3 switching angles, you know this is 180 degree or pi. Clear? And this is your 2 pi. And in pi cycle, in the half cycle, you can say this is 90 degree. So all these 3 angles, alpha 1, alpha 2, alpha 3, or theta 1, theta 2, theta, whatever you can call it as, all these 3 angles now are less than 90 degree. That is one of our constraint. See how the control scheme has been developed, that I am telling you. All these 3 switching angles are less than 90 degree. Is that clear? Because this is 180 degree, half is 90 degree. So less than 90 degree is all the 3 switching angles. And one more important thing, you can see the conditions mathematically you can derive. Alpha 1 is less than alpha 2, and alpha 2 is less than alpha 3, and alpha 3 is less than 90 degree, and alpha 1 is more than, you can say, 0 degree. So all this angle, it may be 7 level, 9 level, 19 level, 25 level, any level you design, all these different levels. See, if you go to any number of steps, any number of levels like this, you can consider this halfway is the 90 degree. So all the angles will be within 0 to 90 degree. Is that clear? So within 0 to 90 degree, you have to consider all the angles. That is one of the constraint now. So taking into account that, you need to form a nonlinear equation. Clear? And this nonlinear equation can be solved by the Newton-Raphel, Gauss-Seidel. They have been developed like many years ago, like you can say 2 decades ago mostly. So people are not now using that Newton-Raphel algorithm because that is not at all easier to implement. One more thing, and Newton-Raphel, there are other problems are there, you know, they require initial guess and all. So these are difficulties in the algorithms. That is why people have developed, leaving this mathematical based approach, people have developed optimization based things. What do you mean by optimization? Here you might have heard, many of us might have heard this algorithms, PSO, the genetic algorithm. These are earlier developed algorithm, I can say, very earlier developed algorithm for selective harmonic elimination. So why we are going for this algorithm? You can ask me why I am going for this algorithm. Where is the equation to solve? What is the algorithm? As I have told you, there are 3 angles, and you want to eliminate, you have an objective here. What is the objective? Now I want to eliminate the harmonic orders. Why I am eliminating only low order harmonics? Because they are dominant in the output voltage of an inverter. The dominant harmonics are odd order harmonics and low order harmonics, not the high order. High order harmonics can be filtered out using a small size filter also. But for a large, for the low order harmonics, you need to focus you cannot connect just a filter, inductor filter to eliminate it. So you need to focus more on that. So you see another point here, because after this mathematical equation, what I will show you, you can understand easily if you understand this one. Here you can see that I have told you there are 3 angles in the 7-level output, alpha 1, alpha 2, alpha 3. There are 3 angles, and if there are 3 angles, how many equations you can form? The nonlinear equation will be 3, right? There are 3 nonlinear equations you can form, and if there are 3 equations to form using 3 unknown variables, how many harmonics you can eliminate, or how many harmonics you can target here. As there are 3 equations, you will have 2 unknown, or sorry, not 2 unknown. You can calculate 2, you can eliminate or target 2 harmonics orders. So it means what? You can target 3rd harmonic, 5th harmonic. 2 order of harmonic you can target to eliminate. Clear? So that way you can proceed here. So we have employed that same rule, whatever I've said. You can see there are 3 equations relating to alpha 1, alpha 2, alpha 3. How we have developed this equation, this is very basics. I don't want to go through it, because in any output of a multi-level inverter can be expressed in Fourier series. 1,000 papers are there on this, you can follow. And for 7-level inverter, I have first equalized one equation with modulation index, because modulation index is the term I told you need to concentrate on. When you vary that modulation index, you need to see what is the harmonics variation. Then another 2 expression I have taken here relating to, because I can take only 3 equations, right? 3 unknowns are there, alpha 1, alpha 2, alpha 3. 3 equations I can take. And as there are 3 equations I can take, 1 equation I have already taken with modulation index equalization. So another 2 equations definitely I need to take for targeting the harmonics. So here I have taken, you can see, 3rd and 5th harmonic. You can ask why I have taken 3rd and 5th, because lowest order harmonic to eliminate is the 3rd. And this is a single phase system what I am talking about. So that is why I have considered 3rd harmonic. Otherwise, if it is a 3-phase application, 3rd harmonic is need to be avoided. You can consider another order harmonic, 5th and 7th maybe you can consider to eliminate. Clear? But the observation or conclusion from here is, if it is a 7-level output, you can focus on only 2 order of harmonics, and you can do only 3 number of equations which are non-linear in nature. You see cos theta 1, cos theta 2, cos theta non-linear in nature. You cannot solve it simply by computation. And also, why you cannot solve it simply by computation? Because you have objective now to eliminate 3rd and 5th. So you need to focus, or you need to develop an objective function, what I have taken here. I will just tell you very simply how I have designed or taken this objective function. Here, this, if you take this values of n and you can put it here, you see. First thing here, I have taken the first term. First term is the fundamental term. That is regulating the fundamental value. Second term is the harmonic. If you put it here, Vn is nothing but the V3, V5. So 3rd harmonic, 5th harmonic, that are taken here. So harmonic components are squared, that are given some importance. And this fundamental component are given much importance. That is why they have taken 4th order, or you can say 4 power, right? The power has been chosen according to importance, first thing. Second thing, this is first term is for fundamental. What do you mean by this fundamental value you want to maintain? You see, I will show you maybe in the output somewhere. Okay, at the end we will see this. Okay, we will discuss that. So this is how the selective harmonic control scheme has been developed, taking into account nonlinear equations, how to solve and all these things. Let us see all this type of this implementation, how it can be done with respect to Arduino. So here we start our Arduino based control implementation. First thing, I will just take you. I will not take time on this controller, because with 700 and 800 rupees you can buy a simple controller, any controller of this Arduino Mega 25, or I can show you here 8 Mega 2560 I have mentioned. 8 Mega is the microcontroller. This is one type of microcontroller, right? And this microcontroller, if you see the pin diagram, you can see there are power pins are there. I'll start with this 3.3 volt, 5 volt power pins are there. So that at any point like this, pins are there, you can take here from wires from here, or you can connect wires to these points, all these points. So similarly, power pins are here. And you have analog inputs. Analog inputs means if you have sensor inputs and all, you can fix it to this. See, in PB applications, MPPT is there. In maximum power tracking, there are many other professors, they have already taught us what we need to take VPB, IPB, right? That is clear, I think. VPB, IPB needs to be taken for calculating the maximum power point. So in that case, VPB, IPB need to sense, and you need to give it to analog input pins. Analog pins are, because of that, it is there. You have some PWM pins you can see, and there are that are digital outputs. And here you have here also this side digital outputs, right? So you might be thinking why I'm talking about this controller, because when you buy it immediately, when you start using this hands-on, definitely you will again confuse if you don't know about this controller. So very basic things I'm telling you, and not telling you about microcontroller logics and all. Very basic things what you need to know, I'm telling you that. So this pins here, you can see there are 54 number of input output digital pins are there. Among 54, 15 here on this side PWM output is written. That 15 are taken for PWM pins, and other pins are for your this other pins are for digital outputs. You can also use these digital output pins for the getting the digital output. Digital output means what? That is the PWM pulse. Clear? You can connect this Arduino with a USB connector to your PC or computer directly. I will show you how to connect. You can go for USB protection is also there inside this. Don't worry about it. Another point I want to highlight here, and the serial communication, you know why these communications are there, to communicate with computer or to any sensors. There are communication ports are there. You can see if it is not clear, I cannot do anything here. But a picture what I've taken, you can see TXRX is written, that is transmitter receiver is there. So serial communication you can also what you can do with this Arduino. I have taken only 2560 because this is one of the advantages one. Because if you compare with Arduino Uno and Arduino, what is that, Micro, they are all consist of very less number of analog and digital output pins, right? You can see in Arduino Uno maybe there are 14 digital output pins. So 14 pins, and if you want to implement a higher number of switches are there, you need more number of pulses from these points. It is very difficult, right? So you need to buy a controller where you can at least give it to all the switches pulses. If you need to give the pulse. Here another point I will show you, that is nothing but your this point here. You see, if it is clear or not, I don't know in the picture. It is read point here it is written L. What is that L? That is nothing but the LED. LED, there is a inbuilt LED on this board that is connected to the pin number 13. There is a pin number 13 here. If you count from 0 here, 0, 1, 2, 3, like that, it is 13 here. And 13 number pin has a inbuilt LED. Why I'm highlighting this one, you will understand after this. So with this, you can go for Arduino controller implementation or programming from, you can download the software from arduino.cc. This arduino.cc software will give you the website will give you the software. You can go for this IDE website. And if you try to download the software, you can write, if you try to write the coding and do this on and try to building means you need to program the controller. Because these are all programmable. So if you program it using your control logic, using this software Arduino CC website, if you download and do that programming, that becomes not somewhat easier, because you want to develop the system in simulation, and after the simulation is developed, you want to test it, right? So we will go through MATLAB simulations one. You see, I'll start with MATLAB based implementation here. A simple thing what you can do, all of you today, if you are having 2018 version or I think upper version in 2017, maybe you can try here. I will just check it. I think yes, mine one is 2018 one. So you can go for more upper version than 2018 or 2017. You can, because the recent one is 2020 is there. So we'll try to finish within 10 to 15 minutes. Don't worry, you will understand everything. You see here, this is a Simulink support package for Arduino hardware, where you can download. There is the link also I've given here. You can go to File Exchange MATLAB Central. If you directly search here in MATLAB Central, if you search here for Simulink support package for Arduino hardware, search in the search tab. Just click search, you will get it. You just click on download. It will ask you for the permission of your what is that called account. You can open a free account in MATLAB. You can download this. First thing, do that. So if you download this, this will give you the Simulink support package. When you have downloaded, this will integrate with your MATLAB version Simulink. And when you download this, you will now open MATLAB. When you open MATLAB, your 2018 version MATLAB, you see on the top there are Simulink button. I don't want to go through this because I believe, or I assume all of us have tried with Simulink. You will find definitely a Simulink button. If you click it, what I want to highlight here is you will find this one. You see, it is written Simulink support package for Arduino hardware. After downloading and installation, you will find this Simulink support package for Arduino hardware, right? Up to this is easy. Then what you can proceed is you just click on the Simulink support package for Arduino. If you click on this, you will find a, what is that called, a help kind of thing you can see in the Simulink. It is available. You see under Simulink support package for Arduino hardware, what is given. There are given some basic model test models. There are given some external models. There are given some closed loop models. Some different algorithm how to implement they have given. Different things, basic things, only basic things they have given. You can utilize that. So that I want to highlight here. Then the main thing you need to know is about the Simulink library browser. In your Simulink library browser, we all know this also is very easy. Simulink library browser, where to open, you know. If you open simulation, there from there only you can open Simulink library browser. So this up to this we know. Simscape, all these things within that, how you will find the components, the different components. You know about MATLAB. I will tell you about this point here. You see, when you download Simulink support package, what will happen with your library? Automatically, these things will be added. Simulink support package for Arduino hardware. So with that, again, you see there are different when this library within library Simulink support package added, this kind of components will automatically appear in simulation, right? Digital input, digital output, analog input, analog output. I told you already how you will utilize this analog pins, digital pins. Then you see, I will focus only on digital input, digital output pins. Digital input, digital output pins will, what it is when you open it, double click, open it, paste it in a new model, Simulink model. When you open, you will see the digital output you focus. It is asking for pin number. What is this pin number? I told you, that is why I've shown you the configuration. 1, 2, 3, the likewise pin numbers are there in the Arduino. You can assign any pin number where you want to get a digital output, PWM output like this. Because this, any controller, even if it is FPGA, even if this space, even if it is DSP, these controllers will give you 5-volt output of PWM pulses only. It cannot give you directly a multi-level output. Do not consider that. As we all know, this is controller. This will finally generate only PWM pulse. It cannot generate a output, right? Not a multi-level output. So you need to focus on that. So this digital output digital output, if you know about the component here placed in the Simulink, then what you proceed is the test model. Let us test a simple model here, blinking of LED. Here a simple model has been tested. You see, I have taken a sinusoidal, you can tell a block I have taken. And here, when you start doing hardware and experimentation, very important thing is your sample time. So sample time, see many important points I'll highlight here. Sample time has been given here, right? 10 samples, 20 samples, you can do it accordingly. So what will that do at the end? I'll tell you. Here at the end, I have taken, you can see the model, how it is developed. I have given 1, and here I have given 0 constant things. 1 and 0 is giving means it is just to, you can make it on or you can make it off, right? So you can just blink the LED if you want to test. And how you can just first do the test on LED? I told you that is why in the first slide, there is an inbuilt LED and connected to 13 number pin, right? If you remember here, I told you in the previous slide, to the 13 number pin, there is a LED connected. And because of there is a LED connected to the 13 number pin, if you see here, I have taken here a digital output block, right? And I also told you where to find this digital output block. Clear? So from this digital output block, when you open, I have set to pin number. Just in the previous slide, I have shown you how to set the pin number. When you set the pin number to 13, on 13 pin, this same can be programmed. Now you might be thinking, how this will be programmed. Now you think this is Simulink model. This is done in simulation. Now you think how this will be programmed to the Arduino. How this can be done? That can be done with the 2 upper buttons, what I have highlighted on the red color. 2 red color buttons I have highlighted here. So you see on the top, I have left hand side, I have highlighted here the Simulink. There is a setting symbol, right? This setting symbol says configuration parameter setting. You need to do some configuration parameter setting. Otherwise, you cannot dump this control logic into the Arduino, because that is the main basic thing now left with you. You need to dump the controller. You have developed in Simulink, and very easily almost all of us can design in simulation. How to dump it? Those settings I'll tell you. This setting symbol, there is very important thing that is called as configuration parameter setting. There is another on the right hand side I have highlighted, that is called as build. If you see on the button here, this button is called as build and run. So what this button will do at the end, if you click this build and run, it will build this program logic, whatever developed here. This program logic developed here in this model will be dumped into the controller, right? So that is the final thing. So this configuration parameter setting, what you will do, we'll see it here. Before that, let us see again how I told you how to connect with the PCB. Sorry, not PCB. How to connect with this PC? I'll show you. So I've connected. You can see with the USB cable. You can connect it to your PC, and this is the zoomed in version of your Arduino Atmega 2560 microcontroller. You see the configuration parameter first. When you click on the setting symbol, the configuration parameter settings will open this one. You can go to hardware implementation directly. See all the steps I am highlighting here, so that you will not miss a single step to implement or to try it with Arduino Mega first. Click on hardware implementation, open this Arduino Mega 2560. You set it, not open, you need to set it here, the Arduino Mega 2560 board, if it is not automatically set. Most of the time it is not automatically set, you need to set it here. So that is the most important part. If you do not set it here, the hardware board, what you have connected to your PC, simulation program will not dump into the controller. Next thing, you can test it, the target hardware resources. Under this, you will find some additional settings that if you do not do also, it is not a problem. That is why I have not highlighted here. What are the additional settings? I'll tell you. Build and run what I told you. Those simple settings you can do. You can set the baud rate of the controller. So that are not required, as I told you. First thing, first try. On the first go, you do not need to try on this. Okay. See now, when I have run this program just in simulation, how the scope, this scope I have connected here, right? How across this scope I am getting the output. Clearly, I've shown you here the scope outputs with different samples. I told you when different samples are varying, that will affect on the output of the hardware, right? When you implement this on simulation or your, sorry, not in Arduino, how this will affect your hardware output, you can see in a simple video. I'll show it to you here. Let me just choose a. Here you can go for this. Yes. So I'll just run this video. You can see the video. How this programming, when I'm dumping it at the end, you see the 13 number pin LED. The L is written right here. When where L is written, you can see there the LED is continuously blinking here, right? At this point. So why this LED is blinking? Because this program has been dumped into the controller. Very simple test we have first conducted to test whether LED is blinking or not, whether program has been dumped to the controller or not, those things. And 10 samples and 20 samples with that, if you see, the pulses are varying from 0 to 1, but here there are 10 pulses kind of thing, and here there are 5 pulses. So it means what? The blinking speed will increase and decrease. That also you can test with varying the controller samples. So this is how we can test first. So immediately, without wasting time, I will show you 2 more slides here. How to implement switched capacitor type multi-level inverter, because time is too much now. I don't think you can spend more time on this, because this is around evening here. You can see the simple circuit diagram I have shown you, and the same circuit, whatever I have explained in detail, that I have implemented in simulation here. You can see I have taken one single source, and I'll show you here what are the sources where I have taken. And there are how many number of switches? Just focus on that. There are 6 switches. 2 switches for generating the levels and 4 switches for generating the output. 6 switches. Logic I have told you, when to on the switch, when to off the switch. I have told you already. That you have understood. Now you will start with that. So this circuit where there are 6 number of switches, that 6 number of switches I have kept it inside this. These are all subsystems, and I will not tell you how to develop a simulation model. I think you all know very much better with that. Pretty much better you can do this. I have done this subsystem where we have placed, if you see S1, S2, these two switches S1, S2, right? And there are 4 switches as I told you, T1, T2, T3, T4. Clear? What is there inside this basic unit is the source part. That I'll show you inside what is there. Then the PWM logic, what I've implemented before dumping into the controller, that is there inside the switching pulse. These are all subsystems. And here, this side, it is very simple. Loads are connected, different load combination I've connected. And through the breakers, where R load, RL load, you can vary, and you can see the output across the scopes. I'll show you that. I think it is clear about the model. If it is clear about the model, let us proceed to now the how it is there, what is there inside this. Clear? Circuit diagram is there in your mind now. 6 switches are there. Let us go ahead. So first thing inside this switching pulse, what is there? How we can develop the PWM pulse? One of the participants was asking, tell me first how to develop the switching logic. Yes. Here, switching logic, for that you see I have connected a clock first. This clock will give me what? Now, whatever simulation time, I think you all know where to give the simulation time, right? If you assign some simulation time on the top of the Simulink model, it will run for that much simulation time. So 0.12 second it is running. That is the clock. Then there is a block here that this is nothing but a MATLAB embedded function block. This block you will find in the Simulink library. You can search it, MATLAB embedded function block, you will find it in the Simulink library. And how many switches are there with you? Just now we have done a simple programming for LED blinking. I told you which pin you need to program, that you need to assign. Clear? I have assigned to 13 number of pin where I have given the PWM pulse. That is why at 13 number of pin, because there is an internal LED that was blinking. So it means that is how you need to do programming. I have taken the Arduino pins here that are all digital output pins. If you sometime refer to this PPT, sometime also you will find out digital output pins. I have also shown you where to assign the pin number. Very simple, right? Digital pins are there where you can assign the pin number. We have assigned the pin number 31, 32, 33 like that up to 5, 6. There are, because there are 6 switches are there. You need to do that. There are how many number of switches, based on that you need to assign. See, when I'm running the simulation, I'm getting the pulses here. Very clearly I'm getting the pulses. Now main thing is that what is there inside this function block then? If you know this, then everything is over. Everything is over if you know this, what is there inside this function block. Because that is what is the logic I have developed here to get the output. If you get this same pulses in the hardware, everything is done. Next, proceed. This is the programming. I told you just now, logic you need to know. I told you at 0 level, which are the switches on. I'm just writing the same code here in terms of 0, 1, that is on and off. 0 is for off, 1 is for on. See, I'll focus on 1 level. In the first step, what we are doing, if you remember, I am turning on S1. So you see, S1 is on, S2 is off. And you are turning on T1, T2. Just focus on the circuit here. T1, T2 on, S1 is on, right? S1 is on for charging the capacitor, T1, T2 on for generating level. So I have just turned on that thing. In the positive half cycle I have given, negative half cycle I have given. Not much time, otherwise I would have explained with you all with the switching table also. But I will not spend much time because this is very in detail. I've explained the circuit diagram maybe, so you can just write the coding yourself. But I have just not highlighted one important thing. If you write only this much in the MATLAB, it will not generate or run it. You need to give a first a reference signal. You can write just 1 line code to take the reference signal sinusoidal. Then from that, I have written this one, right? And after the reference, you can just write these codes and all. You can try it out. You will definitely get the results. So now, main thing is you see here. One more important point, you can see it here. I told you what is there inside this subsystem. Inside this subsystem, these two, basic unit, full circuit. Okay, focus on that. See, basic unit is the source, full circuit is the circuit diagram. See, in the circuit diagram first, there are 6 switches, very clear. 1, 2, these are 4 switches on the load side, and I have 1 diode as in the circuit. Clear? This circuit is now clear, and these 2 points are connected to these 2 points. So that is what is there inside the basic unit. So these 2 points, if you see, I have developed a photovoltaic system at the input side with MPPT controller. There is a boost converter. I think almost all of us know how to develop boost converter in Simulink. Maybe in the BTech level, we almost taught us for how to develop Simulink in the boost converter. But MPPT controller implementation, that you need to focus on. That is not the part of this work, and I will not focus on that. You can develop P&O algorithm, incremental conductance, any algorithm for giving the pulse to this switch of the boost converter. Now you can ask me, because I have told you earlier, this is a switched capacitor type inverter which does not need any additional boost converter, because there is no need of DC-DC converter when you are achieving boosting here, right? Why I have connected again a boost converter here? So there lies the important concept here. I told you, right, when you do an extensive investigation of this work, you will find out the problem with this. So problem is that when you charge and discharge a capacitor suddenly in one cycle, what will happen? The current across this capacitor will rise to a very high value that is called as inrush current for a short period of time in every cycle. So this inrush current will cause the more losses, and also it may damage the capacitor, also some of the switches. So to avoid that, I have in the simulation I have used a boost converter, or else if you don't want to use boost converter, why I have done boost converter, I'll tell you what you can do to avoid this inrush current or high peak currents. You can connect a simple inductor in the charging path. So that is the logic. First, so what I'm thinking, if I just connect an inductor in the charging path, that will no doubt reduce the inrush current to many amperes. To this much you can reduce, no doubt. But the problem is you have to connect an inductor, and in a boost converter, what is the main cost effective part is the inductor, right? So this inductor anyhow you have to use. So that is why I've developed a boost converter where there is inbuilt inductor is there. You know, in boost converter, inductor, capacitor, diode, and switch is there. So one inductor will act for this purpose. And also with respect to that, another purpose is that you can achieve more boosting. You can say 2 times boosting by this circuit, 2 times boosting almost if we are operating with MPPT with this boost converter, and you can achieve almost 4 times boosting, you can say, with this photovoltaic system. I think it is very much clear here. Now let us move to the results. Now you see, when I'm running in the simulation, you are getting the 5 level output as expected, and you can see the capacitor voltage here. I want to highlight there are 2 capacitors I've connected here. One capacitor is this one, which you need to charge and discharge. What is this capacitor? You see these 2 points across the input is connected to here. So this capacitor can be treated as a DC link capacitor, right? So DC link capacitor output and the output the capacitor which is charging discharging, both are same, nearly 40 volt, if you see. Because I told you, right, input source voltage jitna hoga, accordingly your output across this capacitor will appear. The same output you are getting, and that is why you are getting 5 level output. And I'm changing the load. I've told you I've connected R and RL load. When you are running, see the R and RL load change in the current. And because of this change, we have taken harmonic analysis. In the harmonic analysis, you see the harmonics. Generally, in 3 level inverter, the harmonics are almost 35 to 40%, almost. So if it is 40%, I have reduced it to around 18% almost, the output voltage. Current, when it is sinusoidal, after connecting RL load, again I have tested the current THD, almost 3%, which is following the IEEE standard. Clear? So this kind of result and test you can do. Now, main part, what is left, where is the hardware implementation? Because this is simulation, it is implemented. You have got the pulses like this, what I have shown across the digital pins in the 31, 32, 33 pins. Yes. Now let us move to hardware. Here I have in my laboratory, we have here the different switches. And if you know something there to start implementing the basic with the circuit diagrams, there you will find you need a driver. What is the need of a driver? This TLP250 will do isolation, amplification. Because you see this pulses, what you have got is only maximum of 5 volt from the Arduino. Arduino is a maximum operating voltage is also 5 volt. You are getting 5 volt pulse. Can any 5 volt pulse will turn on these switches, these IGBT switches? No. The threshold level of the switches is around 12 volt. Maybe you need to apply that much voltage. Clear? So 12 volt threshold voltage will be given from this driver here, the white color drivers, what you can see. And these are all IGBT switches on board. So again, another important point is that this driver, what is shown here on the left hand side, white color TLP250, how it will get a pulse, because how it will amplify from 5 volt to whatever required voltage of the switch. That amplification or that supply to this driver will be given from another circuit on the right hand side. So that is your supply to the driver, you can say. Here I have used a SMPS kind of configuration. You can say here AC supply is taken and the load output side, this C is giving a constant 12 volt output, nothing else, constant 12 to 15 volt output it is giving this across this capacitor. So that constant voltage, why there are 5 capacitor, you can ask me, I'll also tell you about that, because you can at a time you can give it to 5 number of TLP250 from this point. Are you getting? At a time from this SMPS, you can give it to 5 TLP250 points. So 5 switches can be at a time fired, or at a time can be given supply to these drivers. Now, this is our developed setup here. From the top view, side view, you can see everything. I have used a DSP controller. What I have explained you till now about a Arduino controller, which is the first initial starting stage. You can try it with Arduino. Then you can go for this space, DSP and all I told you. You can see there are nonlinear load we have connected. We have connected the switches with heatsink. That is the same switch configuration what I've shown you. There is only difference here is that there are some switch heatsinks are there to dissipate the heat. And this circuit I've told you, supply to the driver, it is giving here. Okay. Then we have also connected the load combination, R load, RL load. There are also, we have programmable DC supply in laboratory. We have current probes, you know, might be knowing. There are MPPT controllers. Here you can see there is an MPPT controller developed with Arduino controller. And we have also solar simulator in our laboratory. Solar simulator is giving the required, if you do not have a PV panel, right? Because PV panel controlling shading pattern and all, it is very difficult. The solar simulator, if I take again, if I start explaining, it will take another 1 hour. So I'm not going deep inside the solar simulators, how to use it. Maybe this you can buy it in your institute and you can try it. And if you want to know more information, you can just discuss. We'll discuss later on. You see here at the end, I want to just show you with both fundamental frequency control scheme and high switching frequency control scheme, the output we have obtained across the oscilloscope. This is the scope coder. The high power, you can say, high quality results we have obtained here. With difference in the output voltage, the yellow color output, you can see how it is getting the output of fundamental and high switching frequency. Clear? So this is how we have tested our inverters. Again, I want to highlight you one important point. You can go through all these papers. If you have any doubt or you can any question, queries, we must discuss in detail. No time now, so we'll just stop it. So any doubt or any, and one more point, I just missed it here. The control logic, what I have shown you here to implement, this is one type of fundamental one. Clear? I have not shown you here how to implement high switching frequency. Again, because to explain high switching frequency and all, it will take much time. So I have not included here. Time is not much now. Anything you want me to, or you want to share with me, please.
Hello, sir.
Yes, yes.
Sir, many driver circuits are available, sir. You are using TLP 250 driver circuit. Like
Yeah.
that, please, suppose IR2110 is available.
See, IR2110, that is the initial ones.
Yes, sir.
And the TLP 250 is somewhat high power. For high power circuits, you can use it. And if you go for much higher power, maybe around 1.5 kilowatt more than that, then you can go for HCPL 3120. And there are 3120, 316J. These are generally used for IGBT and MOSFET drivers.
Okay, sir.
Any other things?
Yeah, any questions? I think Kaibalya, thank you, but you have given a long hands-on practice means a long hour,
Yes, sir.
maybe
Actually,
So,
more than 1.5 hours,
so
and
this
hopefully,
this class,
uh,
this session will conduct at least 2 hours, 3 hours sessions are next, each, if possible.
we are planning only training program. Okay,
Yes, sir.
we'll
But
go on
here,
training program
main
using
important is
hands-on practice.
how to generate pulse with signals is
Yes,
a
yes, yes.
important
Means
concept.
from the basic means some kind of research module how to implement,
Yes, sir.
starting from the basic to the complete end. That is possible. That will think in the later stage. Okay,
Yes, sir.
that is our idea. And he has done a lot of work in hardware, and
Yes, sir.
hopefully it is much more useful for the new, means I can say the young faculties who are carrying out the PhD work, research work. They can interact with our scholars also. You will get the idea. And these are the Arduino controller, all those things are not so costly also. You can procure and you can test the algorithm. That is possible. When you are working in an institute, hopefully it is not a problem to procure small things. And all of us in a same platform, and hopefully it is going out of time, but sometimes you have to compromise or sacrifice to learn something new or better. Okay, and that way you can also explain to your students and let the everything should go in a very let's say fruitful way. And I particularly thanks to Kaibalya, and he has delivered a good lecture, uh, completing with the multi-level inverter and the hardware. We are happy to get such kind of PhD scholar at MIT Meghalaya also.